Hello, grade 10s. In today's lesson, we will continue on the topic of mechanics. And today we start to understand motion in one dimension. Now, this chapter is very long with many objectives. So we're going to describe the concepts of position and frame of reference or point of origin. We will define distance and displacement. We will calculate distance and displacement for one-dimensional motion. This whole section only deals with motion in one dimension. We will define average speed and average velocity, as well as instantaneous speed and instantaneous velocity. We will calculate speed and velocity for one-dimensional motion. We will learn how to do speed conversions. We will define acceleration. We will differentiate between what makes acceleration positive versus negative. We will calculate acceleration for one-dimensional motion. We will then draw graphs of position versus time, velocity versus time, and acceleration versus time. And we will describe motion for objects that are stationary, meaning that they're not moving, objects that are moving at a uniform velocity, and objects that are moving at a uniform acceleration. We will determine the velocity of an object from the gradient of a position time graph. We will determine the instantaneous velocity of an object from the tangent on a position versus time graph. We will determine the acceleration of an object from the gradient of a velocity versus time graph. We will determine the displacement of an object by finding the area under a velocity versus time graph. And we'll determine the velocity of an object by finding the area under an acceleration versus time graph. Now, motion in one dimension is about how things move along a straight line. And in this section, we're going to learn how to describe motion in one dimension and how to draw and analyze motion graphs. There are three features of motion that we're going to use. One is displacement, one is velocity, and one is acceleration. And as we learned in the previous section, all three of those are vectors. So all three of those have magnitude and direction. So remember that displacement is represented by the letter X with an arrow above it. This arrow represents that the variable is a vector, and displacement is measured in meters. Velocity V is measured in meters per second, and acceleration A is measured in meters per second, or meters per second squared. Now let's talk about position and a frame of reference, also known as a point of origin. When we study motion, we need to consider the position of an object relative to some frame of reference or some point of origin, which would be the frame of reference. So, for example, if you ask your friend Sarah to deliver a chocolate bar to your little sister Jenna in her classroom, you tell Sarah that Jenna sits 2 desks to the left from the classroom door. So in this case, the classroom door is your frame of reference or your point of origin. So that now, based on this point of origin, you may continue to give Sarah directions on exactly where Jenna sits, which is 2 desks to the left from the classroom door, which is the point of origin. If you don't include this frame of reference, then you're not able to properly describe to Sarah where your sister Jenna sits. you can't just say that Jenna sits 2 desks to the left without providing a reference point. Let's define position. Position is a measurement of location with a frame of reference that it has to be combined with. And what is this frame of reference? It is a reference point of origin that is then combined with a set of directions from that point. On a Cartesian plane, we have x and y axes, and we have a point of origin where the two axes meet. Now, on a Cartesian plane, we have positive x values to the right of this 0 point and negative x values to the left of the 0 point. We have positive y values above the 0 point and negative y values below the 0 point. So on this graph, we have 3 positions shown as xy coordinates. So this one over here, this position is represented by minus 2x and positive 4y. This position over here is represented by positive 3x and positive 3y. And this position over here is represented by 0x and minus 3y. But we don't always use a Cartesian plane with x and y coordinates. Any point of origin or frame of reference to describe position works. So let's take a look at this example, and we always have to state a frame of reference and a positive direction. So let's assume that the point of origin is Jay's house, and to the left, meaning towards the school, is the positive direction. So this means that the school is 1 to 300 meters away from Jay's house to the left, and the left is the positive direction. Again, if Jay's house is the point of origin and to the left or towards the school is the positive direction, then Tay's house is 200 meters away from Jay's house to the right, which is the negative direction. Let's take a look at another example. In this case, the point of origin is May's house, and to the right or towards the shop is the positive direction. So that means that the shop is 1, 2, 3, 400 meters away from May's house to the right, which is the positive direction. If we consider Kay's house relative to May's house, well, it is 100 meters away from May's house to the left, which is the negative direction. Now that we understand that, let's define distance and displacement and look at the differences between the two. So what is distance? Distance is the total length that an object has moved to get from its initial position to its final position. Distance is represented by the letter capital D. The SI unit of distance is the meter. Distance is a scalar, so it only has magnitude, no direction. So suppose a fly is trying to get from point A to point B. Now, it might take path 1, path 2, or path 3. The distances are very different. So path 1 represents the longest distance that the fly took to get from point A to point B, and path 2 is the shortest distance that the fly took to get from point A to point B. However, in all three cases, the fly started at point A and ended at point B, and that brings us to displacement. Displacement is defined as the change in an object's position from the starting point to the ending point, and it's always in a straight line. So regardless of the actual path traveled, for displacement, we only consider the straight line distance from point A to point B. Displacement is represented by the letter X. Now this triangle over here means change in displacement because it is the change in position from point A to point B. The SI unit of displacement is the meter, just like the SI unit of distance is the meter. However, displacement is a vector, so displacement has both magnitude and direction. So in the figure above, although the fly traveled different paths, meaning that its distance would have been different had it taken path 1, path 2, or path 3, its displacement is the same in all three cases, because in all three cases, its starting point and ending point were the same. If the fly flies from A to B, and then it flies back to point A, well, it would have traveled some distance based on the total length that it has taken. But regardless, its displacement will be zero because when the starting point and the ending point are the same, then your change in position is zero. It hasn't changed. The delta symbol, this triangle, means change. And change in anything is calculated as final minus initial. So to represent the initial position, we use X with a subscript I, and to represent the final position, we use this X with a subscript F. So the change in displacement is always going to be calculated as the final position minus the initial position. Delta X equals XF minus XI. Now, displacement may be positive or negative, and the positive or the negative symbol will help us to assess the direction that the object is moving. For the same motion, distance and displacement may have very different values. So here we can see some differences between distance and displacement. Distance is a scalar, whereas displacement is a vector. Distance is always positive, but displacement may be positive or negative, and that depends on the direction in which the object moves. Distance, like we saw in the fly example, depends on the path taken, whereas displacement does not depend on the path taken. Displacement's only concerned with the starting position to the end position. So let's explore these concepts in more detail here. Ray walks from his house to meet Kay, and together they walk to school. So the first question is, what distance did Ray cover? Now, for distance, we don't need to state a positive direction and a point of reference. So in this case, we can simply see that Ray walked 1, 2, 300 meters to Kay's house, and then together they walked another 100 meters to school. So the way that we show this calculation is we say D equals 300 plus 100. We always want to break it up into the individual distances that were covered, and that is equal to 400 meters. The next question is a little bit more confusing. What is Ray's displacement And here, when we're dealing with displacement, we do need a reference point and a positive direction. And if it's not given to us, then we can pick any reference point and we can pick either direction as the positive direction. But in this case, we're told that Ray's house is the reference point, and to the left or towards the school is the positive direction. Now remember that we want to work out change in displacement delta x as xf minus xi, the final position minus the initial position. Now Ray's initial position is his house, and because his house is the reference point, then that gets a value of 0 meters. Ray's final position is the school, which is 400 meters away from Ray's house. But remember that towards the school is the positive direction. So it is a positive 400 meters. So the calculation goes like this. Delta x equals xf minus xi, which is positive 400 minus 0, which gives us an answer of 400 meters. Now, 400 meters is only the magnitude of the displacement. We also need to state direction. And in this case, it is in the positive direction, which is towards the school. Now, the moment that we get a positive answer, that tells us that the motion was in the positive direction. A negative answer means that the motion was in the negative direction. Now, we shouldn't answer the second part, the direction part, by stating positive direction or negative direction. We should rather state what we defined as the positive direction. So in this case, we said that towards the school is the positive direction. So in our final answer, when we provide the direction, we'll say towards the school. What is Ray's displacement if now instead the shop is the reference point and towards the shop is the positive direction, meaning that towards the school is the negative direction. Now, the motion is exactly the same, where Ray left his house, walked to Kay's house, and then walked to school with Kay, and we want to know Ray's displacement. So the implication here is that the answer is going to be exactly the same, but the calculation is going to look different. So in this case, this shop over here is the reference point, and to the right is the positive direction. So now we need to figure out what is our initial position and final position so that we may plug those numbers into our formula. Now, in this case, Ray's initial position is his house, but his house is 200 meters away from the shop. Now, the shop is the reference point. In this direction is the positive direction, which means that towards the school from the reference point is the negative direction. So that means that Ray's house is 200 meters from the reference point in the negative direction. So it is minus 200. Ray's final position is the school. Now again, the shop is the reference point, and the school is 600 meters in the negative direction. So the position of the school is minus 600. So now we plug these values into the formula. So delta x equals xf minus xi, which is minus 600 minus 200, which is minus 600 plus 200, which is minus 400. Now we can't leave an answer as negative. A negative answer provides us with a direction. So that means that our delta x, meaning our change in displacement, is 400 meters. The fact that we got a negative answer means that it is towards the school, because towards the shop is the positive direction. So the opposite direction, which is towards the school, is the negative direction. Again, what you'll notice is that the answers to B and C are the same. And that is absolutely expected because we're calculating the same displacement. But the points of origin were different and the positive direction was different. However, that doesn't change the ultimate displacement. It only changes the numbers that we plug into the formula. Let's try another one. May walks from her house to the shop to buy some school lunch, and then she walks to school. So here's May. So she walks from her house to the shop, and then she walks to school. Now, I'd like you to try and answer these questions on your own in the blank spaces in the workbook, and then go over my answers just to make sure that you've grasped the concept. So what distance did May cover? Now, remember that May traveled to the shop and then back to school, and we want to break up her motion. So first, she walked 400 meters to the shop, and then from the shop, she walked 600 meters to school. So her distance is 400 plus 600, which is 1,000 meters or 1 kilometer, but we always prefer to work in SI units. Now, what is May's displacement if May's house is the reference point and towards the school or to the left is the positive direction? So here we only need to consider her initial position and her final position for the calculation. Now, May's initial position is her house because that's the reference point. That means that the value here for xi is going to be 0. May's final position is the school. Now, remember that May's house is the reference point and towards the school is the positive direction. So that means that the school is 200 meters from May's house in the positive direction. So that is the final position. So the change in position, delta x, equals xf minus xi, which is 200 minus 0. So the answer is 200 meters towards the school. Remember, we got a positive answer, so that means a positive direction. And we know that towards the school is a positive direction. Now, we don't take into account May's entire distance. It doesn't matter that she walked all the way to the shops and back to school. Displacement is only concerned with initial position and final position. The next question is, what is May's displacement if the school is the reference point and towards the shop or to the right is the positive direction, meaning that to the left would be the negative direction. Now, again, this is the same motion that we calculated before in question B. So we expect to get the same answer, but our xi and xf are going to have different values. So in this case, May's initial position is her house. May's house is 200 meters away from the school because the school's the reference point, and it is in the positive direction because towards the shop or to the right, is the positive direction. So the xi is 200. May's final position is the school being the reference point. So that point is 0 meters. So now we can plug those values into the equation. Delta x equals xf minus xi, which is 0 minus 200. So we get an answer of negative 200. Now recall that a negative value is there to indicate direction. So in this case, it is the negative direction. Remember that towards the shop was the positive direction, which means that towards the school is the negative direction. And that makes sense because May started off at home and ended up at school. So that means that the final answer is 200 meters towards the school. The negative answer means the negative direction, and if the positive direction is the shop, then the negative direction is the school. This brings us to the end of distance versus displacement. In the next lesson, we will start off by understanding the difference between speed and velocity. So just like distance is a scalar and displacement is a vector, speed is a scalar and velocity is a vector.